The pervasive deployment of advanced manufacturing facilities heralds a profound economic transformation. This industrial expansion promises substantial GDP augmentation, the cultivation of novel export markets, and the generation of high-remuneration employment opportunities. Such unprecedented growth, however, is not without its inherent complexities and potential liabilities. Unfettered industrial proliferation frequently precipitates escalating environmental degradation. This manifests as heightened pollution from factory emissions and the voluminous discharge of waste streams. Concomitantly, societies face increased healthcare expenditures and formidable cleanup costs. I heard that for a second there. One cat asking back cap. Such a deal and justifying that cap. So much trouble is happening. When you hear it, I promise you more information. Furthermore, the environmental burden can lead to a significant devaluation of local real estate. Contaminated land and atmospheric pollutants diminish property desirability and market value. Achieving a judicious equilibrium between net worth accretion and environmental accountability necessitates proactive policy interventions. These interventions include the implementation of robust carbon pricing mechanisms and stringent waste management regulations. Crucially, sustained investment in green technologies is paramount to mitigate ecological impact and foster sustainable industrialization. The contemporary manufacturing landscape is increasingly defined by products inherently suited for fully automated production paradigms. Electronics, for instance, including printed circuit boards, smartphones, and modular components, are ideal candidates for robotic pick-and-place operations. Automotive components represent another significant domain. Engine blocks, chassis welds, and intricate paint applications are routinely executed with precision by automated systems. The consistency and speed achieved are unparalleled. Plastic goods, encompassing injection-molded containers and medical disposables, benefit immensely from automated processes. High-volume production with minimal human intervention ensures cost efficiency and sterility. In the textile sector, fabric cutting and intricate sewing operations are now performed by sophisticated automated cells. This enhances production speed and material utilization. Food processing and packaging lines, from bottling to canning, are quintessential examples of highly automated environments. These systems ensure hygiene, efficiency, and consistent product quality at scale. Advances in machine vision and artificial intelligence now enable meticulous quality control and sorting with minimal human oversight, further augmenting automation capabilities. The integration of sophisticated simulation technologies is revolutionizing factory design and operational optimization. Digital twins, virtual replicas of physical equipment and entire production lines, enable comprehensive testing of diverse layouts and configurations. Throughput modeling allows for the precise simulation of production rates under a myriad of varying operational conditions. This predictive capability identifies potential bottlenecks before physical implementation. Safety scenarios can be rigorously stress-tested within these virtual environments. Emergency shutdown protocols and disaster recovery procedures are validated without disrupting live operations. Energy optimization models identify inefficiencies and potential waste within proposed factory designs. This proactive analysis facilitates the calibration of power consumption for maximal efficiency. Ultimately, the judicious application of simulators significantly reduces capital expenditure. By preemptively resolving operational impediments and calibrating equipment, these tools ensure optimal performance prior to physical installation. The strategic multiplication of inexpensive goods, such as disposable hygiene products or basic consumer electronics, can yield substantial aggregate revenue. This economic model leverages several key principles. Economies of scale are fundamental. As production volume escalates, the unit cost of each item demonstrably diminishes. This cost advantage is a powerful competitive differentiator. The utilization of standardized modules and swappable tooling allows for agile production of diverse stock-keeping units. This flexibility enhances responsiveness to market demands. Just-in-time supply chain methodologies minimize inventory carrying costs. This lean approach optimizes capital deployment and reduces warehousing overhead. Vast output capacity confers significant bargaining power with suppliers and distributors. This enables manufacturers to secure highly favorable input prices and distribution terms, solidifying market position. Interconnected factory networks profoundly strengthen a national or regional economy. Cluster effects, characterized by the co-location of component suppliers and manufacturers, foster an environment ripe for innovation and synergistic development. Large production capacities cultivated within these networks enhance export competitiveness. This enables aggressive pricing strategies in international markets, securing global market share. Such industrial ecosystems are potent engines of job creation. Employment opportunities span from highly skilled robotics technicians to essential logistics coordinators, diversifying the labor market. Technological spillovers are a significant benefit. Research and development breakthroughs in one facility frequently propagate, upgrading processes and capabilities across disparate sectors. Regions that strategically cultivate industrial corridors, exemplified by Germany's Ruhr Valley, consistently demonstrate above-average productivity and sustained wage growth. The benefits of this industrial evolution are not uniformly distributed. Early adopters, whether nations or individual enterprises, are uniquely positioned to capture disproportionate global market share by automating first. Technology providers, particularly robotics manufacturers and developers of advanced AI software, stand to gain immensely. Their innovations are the foundational enablers of this transformation. Logistics hubs, including major ports and freight rail operators, will experience expanded throughput and increased strategic importance. They become critical nodes in the global supply chain. Conversely, economies heavily reliant on manual labor face significant challenges. Without proactive workforce retraining initiatives, these regions risk substantial job displacement and potential trade deficits. Large-scale automated factories necessitate a concomitant evolution in warehousing and transportation methodologies. Warehousing operations are being redefined by autonomous storage and retrieval systems. Dynamic racking solutions optimized by artificial intelligence maximize storage density and retrieval efficiency. This ensures seamless material flow. Transportation paradigms are shifting towards high-frequency, smaller loads. This model enhances agility and reduces transit times. Seamless integration with real-time tracking platforms is becoming indispensable. This provides end-to-end visibility across the entire supply chain. A truly seamless flow from the factory floor to the retail shelf demands both horizontal automation within facilities and vertical automation between them. Autonomous trucks represent a high-potential mode enabling platooning and driverless operations. Their key advantages include 24/7 operational capability and flexible routing, though regulatory hurdles and safety concerns remain. Drones offer medium automation potential for last-mile delivery. They provide speed and bypass road traffic, but are constrained by range limits and payload capacity. Automated rail systems possess high automation potential through smart scheduling. They are advantageous for bulk volume transport and energy efficiency, despite requiring fixed tracks and large capital investment. Conveyor networks offer high automation for intra-facility movement. They provide a controlled environment and low operational costs, but are limited to campus-style layouts. Pilot projects in Europe and China are already demonstrating the viability of driverless trucks on public highways. These initiatives are paving the way for broader adoption. The integration of vehicle-to-infrastructure communications, robust 5G networks, and edge AI processing will be pivotal. These technological convergences will render end-to-end automated logistics achievable within the forthcoming decade. Automated factories will fundamentally reshape retail distribution. They can efficiently supply mega retail hubs, enormous distribution centers strategically located adjacent to major transportation nodes. Alternatively, they can feed urban micro-fulfillment centers. These smaller, highly automated warehouses within cities enable rapid, often same-day, delivery to consumers. Retail will pivot from traditional floor space dedicated to inventory to experiential showrooms. Product will be showcased, but actual stock will reside in nearby, robot-managed depots. Further exploration into the circular economy is crucial for offsetting environmental harm. This paradigm emphasizes resource efficiency and waste reduction. Blockchain technology holds immense promise for enhancing supply chain transparency within automated networks. It provides immutable records and traceability. Workforce transformation, particularly through comprehensive reskilling programs, is imperative for displaced workers. This ensures a just transition in the evolving labor market. The rise of 3D printing hubs as complementary microfactories offers unprecedented customization and localized production capabilities. These angles collectively shape a future where industrial scale, environmental sustainability, and operational agility can harmoniously coexist.